Hey, hello ib1 higher level students. Welcome to my next lesson about relativity. So in the Google Classroom you can find a PDF file with activities, these activities. So please open also this file. After short introduction, we'll be working with this file. So let's start with short revision of our last lesson. We're talking about Lorentz factor. Okay, what is Lorentz factor? Is a kind of mathematical formula which links length and time measured in different frames of reference. So we've derived by using imaginary device called light clock that Lorentz factor is 1 divided by the square root of 1 minus v squared over c squared. Of course, the best is if v is represented as a fraction of speed of light. Then you don't need to recalculate c from, let's say, it's easier to your calculator. You don't need to use standard units because Lorentz factor is something which has no unit. We also plot a graph how Lorentz factor depends on the speed. Okay, if speed is expressed as a fraction of speed of light, then maximum value of speed is equal to 1, and of course Lorentz factor cannot be less than 1. So the shape of the graph is like this. Okay, so Lorentz factor has a huge value if speed goes to c. Okay, I'm not sure, I don't remember, but if we didn't do this, so let's start with writing formula how y, Lorentz factor, depends on x by writing on your calculator something like this. Of course, in this case, c is equal to 1 is a constant, so your x cannot be smaller than 0 and cannot be less than 1. Of course, if x is equal to 1, we have infinite value of y. If x is equal to 0, then we have Lorentz factor y equals to 1. So please create this function on your calculator and make x from 0 to 1 and y, let's say, from 0 up to 10. Then you will see the shape very similar to this one. Okay, so when you will do this, please turn video again, and we'll be talking about length, conduction, and time dilation. So topic is length, contraction, and time dilation. Okay, first of all, I hope that you remember that both time and length measured by different observers can be different. So at first, let's focus on the definition. What the proper time is. So write a proper time. Okay, so let's imagine two observers, which each has a clock. So observer A, let's imagine that this observer runs with clock. Okay, and observer B, who is stationary due to the observer A, and it has also a clock. Okay, in relativity, time of the event of these two observers will be different. Let's imagine that you have an event, something which happens in one place and stationary due to the observer B. Let's imagine that this is, I don't know, a spark or something. Okay, or fireworks or something like this, which starts at one time and ends at other time. And both observers, and A and B, measure the same event. The beginning is when this firework starts to work, and the end of the event is if it stops to work. Okay, so let's look. Observer B is stationary due to the event. observer A runs, which means that the beginning of the event due to observer E is in one place in space, and end of the event due to the observer A is in another space, in another place of the space. Okay, so proper time is one measured by observer who is stationary due to the event. So write this. This is definition of proper time. Is a time interval, a time of an event, not interval, time of an event. Okay, measured by observer who is stationary due to the event. Okay, it's very important because time measured by observer who is moving due to the event is different than time measured by the observer who is stationary due to the event. So in this case, in this particular example, B measures proper time. Okay, due to this definition, because for B, the event starts at the same point at space as it finishes. For A, event starts at different point in space and finishes at a different point in space because there is a relative displacement between A and this fireworks. Okay, so why is it important? Because there is a connection between time measured by observer and time measured by observer who measures proper time. Okay, so due to the relativity, time of an event or time interval, doesn't matter, yes, t or delta t, is always Lorentz factor multiplied by this proper time. So basically, proper time is the shortest possible due to this definition. Okay, proper time is the shortest possible because if Lorentz factor is a number which is 1 or more, then this delta t, any other time which is not proper, will be always bigger than delta t0, than proper, because due to the multiplication, due to this multiplication by a number which is bigger than 1, it must be longer. Okay? So Lorentz factor, remember, is a link between proper and not proper, and proper time is the shortest possible. Okay, so what is a time dilation? Time dilation is this effect that observer who moves due to the event measures different time interval of the same event. Basically, 1 second for observer who is stationary is different than 1 second for observer who is moving, which means that absolute time doesn't exist in relativity. Okay, remember about this. Okay, please copy this to your notebook. When you will be ready, it will be point number 2, called proper length. Okay? So point number 2, proper length. Okay, I'm going to use L with index of 0. And the same, let's imagine that you want to measure the length, okay? And you have 2 observers. One which measures the object stationary due to the object, and second with which moves. So again, you have observer who runs, okay, and observer who is stationary. Of course, all is relative. And let's imagine that there is something which must be measured. Okay, we want to measure this length. This is the wooden block or whatever, doesn't matter. Okay, and in very similar way to proper time, we can define proper length. Okay, is the length of an object measured by observer who is stationary due to the measured object. Okay, and in similar way, similar way to the proper time, we can link length of the object measured by observer who is moving due to the object with length which is called proper length. In this case, who is stationary due to the measured object? B. So in this case, B measures proper length. For A, during measurement, this object displaces. At the beginning is here and end is here. At the end, we have opposite situation. And what is a link between proper and not proper? Proper length divided by Lorentz factor gives length measured by observer who moves. Okay, so in opposite way, in this case, L0, so proper length, is the longest possible. Okay, so in the case of proper time, T0 was the shortest possible time, proper time was the shortest possible time. In the case of length, L0, the proper one, is the longest possible. Okay, it's not definition, but it's easy to remember, longest possible. Okay, and again, the Lorentz factor is a link between these two lengths. Okay, so what is a length contraction? Length contraction is an effect when observer who moves due to the measured object measures different length. Okay, for him, length is contracted, is shorter. Okay. So please copy this as point number 2, and I'm going to present, in my opinion, a very, very, very good example. Okay? So when you will be ready, go forward. So write example. Okay, let's imagine that you have a runner which runs for 100 meters. This is start, this is finish. Okay, start, finish. Okay, our runner starts at start. Okay, and runs very, 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 very fast towards the finish line. Okay, let's name him R. And runner has own clock which measures time R, time of runner. And let's imagine that you will have a lot of fans. Other observers who are stationary, fans, so hands up, yes? Okay, with transparency, run faster. Okay, all are stationary. Okay, these observers only observe runner. And these observers, let's name these observers F, like fans. Okay, and fans have also own clock, just one. I'm going to create clock in one fan. All are together, all are stationary, and all observe a runner who runs from start to finish. Is it clear? Okay, and now the idea is who, runner or fans, or which observer or runner or fans measure a proper time and which observer measures the proper length. Okay, so let's focus maybe with the length. Okay, the length, of course, in the case of distance between start and finish. So who measures proper length? Okay, think for a moment, and then you try to answer. Okay, so proper length is length measured by fans. Okay, I hope that you have this answer. Let's look. For fans, when a runner runs from start to finish, start during this event, when a runner runs, the start is always at this position and finish is always at this position. Is it clear? So for fans, this length between start and finish must be proper. How does it look? How does the length look from the perspective of runner? Let's look. At the beginning, start line is here and finish line is here. Okay, and at the end, finish line is here. He crosses finish line. For him, finish line is here. And start line is back. Okay, so again, at the beginning, start is at the position where the runner is, and finish line is at the front of him. At the end of an event, start line is displaced, is back out of the runner, and finish line is at the position where runner is at the end of the run. So let's look, both end start line was displaced from him back to him, and finish line from front of him towards him. So a runner during run cannot measure proper length. Okay, for fans, start line and finish line both are always at the same positions. For runner, not. So proper length is measured by fans, and not proper length is measured by runner. Okay, now the same with time. Okay, who, or runner or fans, who measures proper time? Think for a moment and answer. Okay, proper time is measured by runner. Why? Because let's look. For him, he has own clock, which is always with him. Remember that event is he starts here and travels here. So for runner, the clock which measures time of this event is always at the same position. I don't know, 30 centimeters from his nose, in his hand, always at the same position. What happens with fans? For fans, the beginning of the event is here at this position, and end of the event is here. So in the case of time, there is displacement. A runner displaces. Okay, so the beginning of the event takes place at a different point in space as end of the event. So fans cannot measure proper time. So not proper time is one which is measured by fans. So again, in the case of length, proper length is measured by fans because for fans, start and finish lines both are always at the same position in space. But not proper time, because the beginning of the event, the runner, is a different point at space than end of the event. Okay? In the case of runner measures proper time. Okay? For him, his clock is always with him, and cannot measure proper length, because at the beginning, start line is at the position where he is and the finish line is at the front, and at the end of the event, finish line is at the position of his position, and start line is back of him. Okay, so you see, I hope that this example is a very, very good explanation of difference between proper time, proper length, and proper time, proper length. Okay, so now please open this PDF file I've attached. Okay, you have 3 questions. Now we have to focus on exercise number 1, but not C. Okay, so we'll be doing exercise 1A, 1B, 1A, 1B, not 1C. Okay, don't focus on 1C at this moment. And we'll be doing 2A and 2B. Okay, and exercise number 3 will be your homework. So now you have for 1A, you have 1 point, and for B, 2, 3, 4, 5, 6. And for second, 1, 2, 3, 4, 5, 6, 7. So together you can collect 13 points. So let's spend with these 2 exercises, with exercise number 1 and exercise number 2, 25 minutes. So please stop video for 25 minutes and try to do these 2 exercises except 1C. After 25 minutes, okay, so let's say 30 minutes, please turn video back again, and I'll be solving with you and you will be checking. Okay? So please stop video and start to do this. Okay, 25 minutes later. I hope that you have. So let's check together. Define proper length. Okay, so what the proper length is? The proper length is the length of an object measured by observer who is at rest relative to the object. So you have this definition in your notebook. It was not difficult, it was not challenging. Okay, B, little bit more, longer, so a little bit more difficult probably. We have, let me copy this to new file here. Okay, so exercise number 1b. A spaceship is traveling to the right with speed of 0.75 c through a tunnel which is open at both ends. Observer A is standing at the center of one side of the tunnel. Observer A, for whom the tunnel is addressed, measures the length of the tunnel to be 220 meters. Okay, observer A measures the length of the tunnel and the length of the spaceship to be 200 meters. Okay, the diagram below shows this situation from the perspective of observer A. So observer A, for him the tunnel is stationary, measures the length of the tunnel to be 240 meters and length of the spaceship as 200 meters. Okay, and we know that this spaceship travels with speed of 0.75 c. Okay, and now observer B. Observer B, for whom the spaceship is stationary, is standing at the center of the spaceship and first calculate the Lorentz factor. Okay, it's not challenging. Lorentz factor is given by formula 1 over 1 minus v squared over c squared. You have only one data, v. V is 0.75, 0.75 squared divided by 1 squared because 0.75 is relative to c. So you have 1 over 1 minus 0.75 squared. Let me use my calculator. Okay, so 0.75 squared is 0.5625. 1 minus this, the square root and reciprocal. So we have 1 divided by the root is here, and we have 1 minus 0.5625, which is 1.51. Okay, I hope you have the same Lorentz factor, 1.51. And next, calculate the length of the tunnel according to observer B. Okay, so let's look. Observer B is in motion due to the tunnel. So for him, yes, length of the tunnel is not proper. Observer A measures proper length of the tunnel. So it will be L0 divided by Lorentz factor. So for A, length of the tunnel is 240. Lorentz factor is 1.51. 240 divided by 1.51 gives 158.9, so around 159, so around 160 of meters. Okay, so observer B measures the length of the tunnel as 160 meters. Okay, and next is here. Calculate the length of the spaceship according to observer B. Okay, now let's look. Observer B measures the length of the spaceship as a proper length. So for B, the length of the spaceship is a proper one. So we have to find L0. Okay, what is L0? L0 is Lorentz factor by length of the tunnel measured by observer A, who is not stationary due to the tunnel. Observer A measures length of the tunnel as 240 meters, and wait, again, we have to find the length of the spaceship according to observer B. So again, according to observer B, spaceship has a proper length. We know length of the spaceship measured by observer A, for whom spaceship is not stationary. So A doesn't measure proper, B measures proper. So we have to multiply Lorentz factor 1.51 by the length of the tunnel, the length of the spaceship measured by observer A, which is finally around 300 meters. Okay? And next, here, according to observer A, the spaceship is completely inside the tunnel for a short time. State and explain whether or not, according to observer B, the spaceship is ever completely inside the tunnel. Of course, let's look. Here we have the length of the tunnel according to observer B, and here we have the length of the spaceship according to observer B. So let's look. For B, length of the spaceship is bigger than length of the tunnel. So what is the conclusion? Not, because spaceship is longer than length of the tunnel. Okay, and this is the answer for exercise number 1b4. I hope you have the same result. Okay, let me change slide and let's solve exercise number 2. We have to omit C and exercise number 2. Okay, let me take this to new slide and let's do this. This question is about relativistic kinematics. A spaceship leaves Earth at a speed of 0.8 c and travels, as measured by observer on Earth. It heads towards and continues beyond a distant planet. The planet is 52 light years away from Earth as measured by observer on Earth. So this situation is illustrated on this graph. Okay? When the spacecraft leaves Earth, Amanda, one of the astronauts in the spacecraft, is 20 years old. The Lorentz gamma factor for speed of 0.8 c is gamma equals 5.3. And what is first question? You have to find the time taken for the journey for the journey to the planet measured by observer on the Earth. Okay, so this first one here. Okay, so let's look. What do we know? We know that planet is 52 light years away from Earth measured by observer from the Earth. So observers from the Earth measure the proper length between Earth and the planet. We know that Lorentz factor is given, and the question is about time. So we have to find time, we have to divide distance by speed. Okay? Speed is distance over time, time is distance over speed. So which distance? So we have to find measured by observer on the Earth. So distance measured by observer on the Earth is 52 light years, and speed of the spaceship is 0.8 c. 52 over 0.8 is around 65, and the unit is years. Light year divided by speed of light, expressed in speed of light, is 1 year. Remember about these three units links together. Yes, if distance is in light years, velocity is in c, then time will be in years. And again, speed is distance over time, time is distance over speed. 52 light years is a distance measured by observer on the Earth, divided by speed, which is 0.8 c measured by observer on the Earth, results in 65 years. Okay, exercise number 2. The distance between Earth and the planet measured by Amanda. Amanda is an astronaut. Amanda is in the spaceship. Okay, what is distance for her? So she measures distance which is not proper. So distance for her, or length, is a proper one divided by Lorentz factor. Okay, so proper one is 52 years. Lorentz factor, light years. Lorentz factor is 5 over 3 is given. 52 times 3 divided by 5 is around 31 light years. Okay, so again, the idea of this exercise is to identify who, or Amanda, or observer on the Earth, who measures the proper distance. Proper distance is measured by observer on the Earth. We have to find the distance measured by Amanda. Okay? Exercise number 3. Amanda's age as the spacecraft goes past the planet according to Amanda. Okay. So now we have to find, we know that Amanda is 20 years old, but first of all we have to find time needed to travel from Earth to planet by Amanda. Okay? So let's look. Time needed to travel from Earth to the planet by Amanda. We know that Amanda travels 31 light years with speed of 0.8 c. So for her, time is this L divided by velocity, so 31 light years divided by 0.8, which gives it is around 39 years. So 39 years is time needed to travel by Amanda from Earth to the planet by Amanda. And we know that Amanda is 20 years old. So finally the final answer is 59 years old. Okay, she has 20 years and needs 39 years to travel. So 20 plus 39 results in 59. So she's 59 years old. Okay, next question. Okay, the last one. Oh, this is challenging. This is quite difficult. Okay, as the spacecraft goes past the planet, Amanda sends radio signal to Earth. Calculate, measured by the spacecraft observers, the time it takes for the signal to arrive the Earth. Ho ho ho, so it is a kind of challenging and difficult exercise. The idea is that we have to describe the situation from the point of view of the spacecraft. In the question, we have to refer measured by the spacecraft. We have to refer to the spacecraft observers, so due to the Amanda. So let's look. Amanda, in her spacecraft, passes the planet. Okay? And she is at a given distance from the Earth. Wait a moment. This is planet. Yeah, this is Earth. And what is distance between Earth and planet measured by Amanda? Distance between Earth and planet measured by Amanda is this. 31 light years. So from the perspective of Amanda, this distance is 31 light years. But from the perspective of Amanda, Amanda is stationary and her spacecraft is stationary. Earth moves away with speed which is 0.8 c. So if radio signal travels towards the Earth with speed of c, Earth, let's say, escapes from this radio signal with speed 0.8 c. So let's look. When the radio signal is here, okay, Earth is displaced. Earth moves. Earth is far, far, far away from this position because Earth travels with speed 0.8 c. Of course, distance between radio signal and Earth is reduced all the time. And finally, this radio signal catches the Earth. Okay, and we have to find this. In my opinion, the best is to divide this exercise into, or this distance into two sections. Yes, let's look. This section, okay, has 31 light years in the case of distance. And what is this section? Okay, this section is something like a distance traveled by radio signal, okay, in given, or other words, okay, let's look. I'm going to add one more distance. This distance is distance traveled by radio signal, Okay, total distance traveled by radio signal. Radio signal travels with speed c, and it takes time t. So distance traveled by radio signal in time t is c times t. Speed times time gives distance. Okay, at the same time t, Earth travels distance which is equal 0.8 c times t, because speed of the Earth is 0.8 c. So speed times time gives distance. So let's look. This short distance is 0.8 c times t. This long distance is c times t. And this separation, initial separation, is 31 light years. So finally, you can write equation that 0.8 ct plus 31 light years is equal to ct. Okay? If distance is expressed in light years, it means that c is equal to 1. So we have something like this. 31 is equal 0.2 times t. So what is a time needed to travel this distance? It's 31 divided by 0.2. So 31 divided by 0.2 is 31 times 5, which is around 160 years. Okay? So around 160 years. Yeah, this exercise is challenging. The second part, this B, is challenging. So let's focus on the solution one more time. Okay, copy this to your notebook. You must understand this. Your homework is exercise number 3 in attached file. Yes, so your homework is whole exercise number 3. The last part is very similar to this we did here. And now our next meeting, on our next lesson, I'm going to create a kind of test. Yeah, I'm going to generate some grades related with Lorentz factor, proper time, proper length. So be prepared. It will be probably in 2 weeks, because in 1 week yeah, we have a free day. So please read this carefully again. You can of course watch this movie with my solution one more time. If you have any questions especially to this exercise, please ask me in a comment below this movie in the Google Classroom. Remember about your homework, it's obligatory. So thank you for watching, stay at home, and goodbye.